Welcome back. So today we're going to talk about parallel search algorithms. And we'll see how to use these algorithms to solve discrete optimization problems. So a discrete optimization problem is a problem where we try to optimize over a discrete set. So for example, the set of integers. Okay, and within the set, we're going to define a subset S, which is going to be, it can be either finite or infinite, but it's going to be the set of feasible solutions to the problem. Okay? And the feasible solutions have to satisfy certain constraints. And then we have a cost function f defined on the set S, and then we're trying to find the member of S which produces the best value for f. Okay, so this is a very general framework for problems, and it covers a very large range of problems. For example, in operations research. So we have many planning problems and scheduling problems, layout problems, logistics and control problems, and different types of satisfiability problems that can all be phrased as discrete optimization problems. So we can consider either maximizing f or minimizing it. So today we'll just select to focus on the minimization problem. So, so again, what we're trying to do is to find a element of S, x star, such that this f of x star is no more than f of any other element of S. Right? So we're basically trying to find the x star which minimizes f. Okay, so so many of these discrete optimization problems are NP hard. Okay, so for example, many planning problems or scheduling problems or satisfiability problems, they're NP hard to solve. Okay, so so that means that we cannot try to find optimal algorithms to solve these problems. Instead, we're going to focus on heuristics. Okay, so these heuristics are basically they'll do some sort of search over the set of feasible solutions. Okay, and the search space is usually very large. And so we want to use parallel algorithms to help speed up this process. Okay, so now when you conduct this search for a discrete optimization problem, you can often model this by a graph. Okay, so the graphs, so the nodes of the graph are going to be these solutions, possibly infeasible solutions for the problem. Okay, and then we're going to make edges between nodes which are sort of close enough to each other. So we're basically searching through all possible solutions for this problem, right? But we're searching through this in a structured way, which is modeled by this graph. And we're going to traverse this graph somehow, and then that's going to take us through all of the possible solutions. And we want to traverse this graph in an order, in a fashion that can quickly find the solution. Okay, and these states can be can have costs. So the feasible or infeasible solutions can have costs, and then this can be modeled using weights on the nodes or the edges. Right, and then yeah, so the overall process is that we're going to traverse through these possible solutions in some order in order to find the best solution. And sometimes if we get to a state where we cannot progress beyond that state, then we're going to call this a terminal state. And otherwise, it's going to be a non-terminal state. Okay, so as a concrete example of this, suppose we try to solve this problem. Okay, so this is a discrete optimization problem called the 8 puzzle. So so basically, we're given this 3x3 square over here, right? And then each of these squares has a number in it. And what you want to do is, so initially the numbers can be in some arbitrary order. And what you want to do is eventually get these numbers into the proper order, like 1, 2, 3, 4, 5, 6, 7, 8. Okay? And also, there's one of these squares that's blank. So that's being represented by this little white square here. Okay? So you can use that blank spot in order to move nodes around. So for example, if you move the blank spot upwards, right, then that's going to shift the 5 downwards. Okay, so then that's going to place the 5 over here, and it's going to place the blank over here. Okay, and by moving this blank spot around, then the hope is that eventually we can get all of these squares into the right order: 1, 2, 3, 4, 5, 6, 7, 8. Okay, so yeah, so there's not really any sort of good algorithm for solving this in the most efficient way. So therefore, we're just going to go for we're going to use a search algorithm to do this. Okay, so now for the search algorithm, we're going to model this using a graph, and the nodes of the graph are just going to be states of this problem. Okay, so so possible solutions to this problem. So for example, you know, the initial configuration, this is going to be one of the states of the graph. And then we're going to make, so there are many possible configurations or states to this graph, and we're going to connect two nodes if they're sort of, if we can get from one node to another using one move of this puzzle. Okay, so for example, if we just move this this blank spot by up one spot, right, then we can get to this configuration, right? So therefore, these two configurations are connected by an edge. Okay, and likewise, if you move this square to the right by one spot, or I guess to the left by one spot, right, then you can get to this configuration, and so these two things are also connected by an edge. Okay, but there's no way to get from, for example, this configuration to this configuration using just one move of this blank tile, and so so there's no edge between these two things. Okay, so yeah, so basically this shows a bunch of different configurations of this problem, and then the connections are between the ones that you can go to using one move of the tile. Okay, so this is one example of a discrete optimization. Another type of discrete optimization problem is what's called a mixed integer program. Okay, so so I'll just show you the example to make it easier to talk about. So for the mixed integer program, what we have is we have a linear objective function over here. Okay, so it's a function in a bunch of variables, and it's a linear function. And since we're talking about minimization problems, let's say that we're trying to minimize this function. Okay. And then also we have a bunch of linear constraints over here. Okay, so these these variables have to satisfy some of these constraints. And yeah, and for this, so if we don't put any restrictions on the variables, so if we allow the variables to be any arbitrary, like real numbers, positive or negative, okay, then this is a linear programming problem. Okay. However, for the mixed integer program, we require that some of these variables have to be integers. Okay. Yeah. So now for linear programming, this can actually be solved efficiently in polynomial time. Right, so polynomial in the number of variables that we have. However, if you require that some of these variables have to be integers, then this problem now becomes NP-complete. Okay, so and in fact, you can use these mixed integer programs to model many other model many other NP-complete problems. So this is a very general framework for solving problems, right? And this is why it's important. Because if we can somehow come up with like fast methods, maybe not necessarily polynomial time, but some sort of fast heuristic for solving these MIPs, right, then we can apply them to many other problems and solve those quickly. Okay, so yeah, so then this is a discrete optimization problem, and okay, so before I show you the sort of how we model this problem, let's just sort of for simplicity, let's require a few things. Okay, let's make a few assumptions. So first of all, let's assume that all of these constraints here are like greater than constraints. Okay, so they have to be larger than some value over here, right? And then also let's represent the set of all these constraints, right? Let's use a matrix to represent that. Okay, so the matrix would so here it's going to be you know, a 3x4 matrix. Okay, and the values in the matrix are just the coefficients for all of these constraints. Okay, and then let's so we're going to call that matrix A, and then let's call the right hand side over here B. Okay, so this is some sort of vector, and like B sub I is going to be the ith value. Right, so this is like B sub 1, B sub 2, and so on. Okay, so all right, so the way we're going to model this problem is that right, so these states of this problem are going to be assignments of values to the variables. Oh, and in fact, for simplicity, let's assume that all of these variables are required to be integers. Okay, so we don't allow any real values, any real valued variables. We only have integer variables. And furthermore, let's just say that these variables have to be either 0 or 1. Okay, so they're binary values, basically. Now, even with all of these assumptions, the problem is still NP-complete. Okay, so yeah. Okay, so then the states of this problem are going to be assignments of values to the variables. And also, we don't require that you assign values to all the variables. Okay, so sometimes you could have variables which are so-called free, so they don't have a setting yet, right? They're not. You don't say whether they're 0 or 1 yet. Okay, and the ones which do have a setting, we're going to say that they're fixed. Okay, so the way we're going to model this as a search problem is that we're going to start with the initial configuration where all of the variables are free. Okay, so we don't have settings for any of these variables. And then we're going to go through these variables in some order. And at each state, we're going to take one of these unset variables and set it to either 0 or 1. Okay, so that's going to produce a new state, right? And then since these two states only differ in the setting of one variable, we're going to connect them by an edge. Okay, so then if you do this, then this is actually going to produce a very large search space, right? In fact, it's going to have since every variable can have 2 settings, and if you have n variables, it's going to the search space is going to be 2 to the n. Okay, so that's too large to actually search through. So what we can do is we can actually try to eliminate parts of this search space, right? And there are different ways that you can do this based on different pruning heuristics. So one simple heuristic we're going to use is that in order for the solution to be feasible, then we have to satisfy all of these constraints over here. Okay. So now, in order to satisfy these constraints, what we're going to say is that so if you look at all of the fixed variables, right, so they already have settings for either 0 or 1. Okay. So then what you're going to do is you're just going to add up the values for these fixed variables. Okay, and the values are given from these A matrices, right? And then so for the ith row of the A matrix, if you take the corresponding variables, right, and you add them up, okay, so then you get this value over here. Now for the remaining variables that you haven't set yet, right, so those can either be 0 or 1. So if they're 0, right, then you're just going to get a value of 0 from that variable, right? So for example, if you set x1 to 0 over here, then this 5 times x1 is just 0. However, if you set it to 1, right, then you're going to get the value aij. Okay, so for example, if this guy gets set to 1, you get 5 over here. If this guy gets set to 1, then you get a -1 over here. Okay. And now, since we're trying to make sure that these values add up to larger than something, okay, so then we want these things to be as large as possible, okay, so meaning that if you have a negative value over here, right, then sorry, if you have a negative coefficient in the A matrix, okay, then you would rather set this to a 0, okay, so that way at least you get a value of 0 as opposed to something negative. So now when you do this, when you take all of the free variables, and then you can set them to either aij if it's a positive value, or 0 if it's a negative value, right? And then you add that to all of the variables which are fixed, right? Then you have to make sure that you can satisfy all these constraints, okay? And if you cannot satisfy the constraints when you do this, right, then you're at a node which cannot lead to any feasible solutions. Okay, so as an example of this, suppose we're at this node. Okay, so in this node, we've set x1 to be 0. Okay, so now this, so when you set x1 to be 0, right, then you get a 0 over here, right, and then you get a 0 over here and a 0 over here. Okay, so now what we need is that for the remaining variables, right, the maximum value. So then we're going to put x1 equals 0 over here, right? So x1 equals 0. Okay, and now for the other variables which we have not set yet, right? Because at this node we still haven't set x2, x3, and x4 yet, right? So now you can set these to be for each constraint, you can set them to be as large as possible, right? Either aij or 0. So if you do this for, let's say, the first constraint, okay, so now you can set all of these x's to 1s, but even in that case, you see that you're getting, let's see, 2 plus 1 plus 2, okay, so that's only 5. Okay, so even if you set all of the variables to be as large as possible, you cannot satisfy the first constraint, okay? You can satisfy the other constraints, but you can't satisfy the first constraint, okay? And so because of that, then this node is an infeasible node, right? And it doesn't have any children which are feasible either, because all of the children will not be able to satisfy the first constraint either. Okay, so therefore we can prune this node. All right, so and you can do pruning in other cases also. So for example, if you were over here, okay, so then we set x1 to 1, right? So then this here we get a 5, right? Let's write that a bit nicer. Okay, here you get a 1, right? So here you get a 1, and then here you get a 3. Okay, but then you set x2 and x3 to be 0, right? So you get a 0, 0, 0, a 0, 0, 0, right? And so now this node, you see that when you're at this node, again, you cannot satisfy the first constraint because even if you set this x4 over here to be a14, right, which is going to be 2, right, you only get 7, so you still cannot satisfy this constraint. Okay, so we can also prune over here. Okay, so yeah, so depending on what these values are, right, as you form the search tree, you can actually prune out large chunks of it. Okay, so instead of an exponential number of values, you can actually go through far fewer values. Okay, so now let's talk about, in general, how do you search one of these, let's talk about the structure of the search graph first, okay? All right, now sometimes your search graph is going to be a tree. So if it's a tree structure, then for every node, there's only one way to get from the starting node, which is the root, to any other node, right? So it's got a unique path, okay? And it's also got a unique cost, right? The cost is determined by the path from the root node to a particular state. Okay. However, sometimes you get that your search space is not a tree, okay? And in that case, there can be several paths to a state. So for example, you know, if your search graph is like this, right, then to get to node 7, there are 2 paths. Okay. Now it's usually easier to deal with a search tree as opposed to a search graph. Okay. So if you have a graph where you can have multiple paths to a node, then you can actually convert that to a search tree. And the way you do that is you're just going to duplicate some of these nodes. Okay, so for example, there's a path going from the left over here to 7, right? And there's another path going from the right. Okay, so then we're going to take these 2 paths and then you're going to break them apart and then use those to form a search tree. Okay, so then for example, in this search tree, right, we have the left path over here and then we have the right path over here. Okay, and then once you do that, now you can use these more sort of easier to develop tree-based search algorithms. Okay, now you have to be careful when you do this because sometimes when you unfold a graph, it can get much, much larger. Okay, so for example, if you have something like this, okay, so now for each node, there are multiple paths to get to that node. And so for example, if you look at this node 10 over here, okay, so there are actually, there are 8 different paths to get to 10. Okay, and the reason is that, you know, to get to 10, we need to go through 4 and 7. Okay, well, there are 2 ways to get to 4. And then once you're at 4, there are 2 ways to get to 7. So that means in total, there are 4 ways to get from 1 to 7. Okay, and once you're at 7, there are 2 ways to get to 10. So, so there are 8 ways in total to go from 1 to 10. Okay, so in fact, if you unfold this into a search tree, right, then you're going to get a much larger search tree than your original search graph. Okay, so you have to sort of be careful when you do this process. Another issue with another difficulty with search graphs is that you can discover the same node multiple times through different paths. Okay, and then so and sometimes you don't want to have these multiple discoveries. Okay, so when you run a search algorithm on this search graph, you can use some sort of duplicate detection algorithm to see whether you've already discovered a node. So for example, you can store all the nodes that you discover in a hash table. Okay, so that way, if you if you discover 4 once through this path, and then a second time through the second path, then the second time you see that 4 is already in the hash table, and you know that you detected a duplicate. Okay, and since there are multiple paths there could be multiple paths to a node, then the cost to a node is going to be the minimum cost among all the paths. And so as you find different paths, right? So as you do this search process, you find different paths, and then you're going to update the costs to a node as being the minimum path cost that you discovered up to now. Okay, so then your hash table can store not only which nodes you've discovered, but also the minimum cost to that node that you've discovered. Okay, so now we're going to talk about several sequential heuristics for searching through these search spaces. Okay, and then later we'll talk about how to parallelize these sequential heuristics. Okay, so the first heuristic is going to be called branch and bound. Okay, so yeah, so the idea is, so this is some sort of pruning heuristic. Okay, so it's going to search through the search graph in some order, but then at certain points in time, we can eliminate certain nodes from ever being explored. Okay, so so now suppose you're searching through this graph, then at some point you have like a frontier of nodes that you've explored. Okay, so suppose you're exploring this the search graph, right? Then you have this frontier, let's say, of there are a bunch of nodes that these are like the farthest nodes that you have explored. Okay, so now for each node on the frontier, potentially this node has a bunch of subnodes that we need to explore. Okay, right? So yeah. So our question is, do we need to actually explore the subnodes from each of these frontier nodes? Okay, so to know that, we're gonna maintain a pair of values at each one of these frontier nodes. Okay, so let's say that you have a value, you have a node P over here. So we're gonna maintain 2 values, M of P. Let's write this somewhere else. So actually, let's just pick one of these nodes over here. Let's erase all this stuff to make it easier to write. Okay, so let's say that we're gonna focus on this node over here. Okay, so we're gonna keep 2 values, M of P and then little m of P and then big M of P. Okay, and what these are going to represent is if you look at all of the nodes that can that come out of this node P. Okay, so all of the possible descendant nodes from node P. Okay, so M of P is going to be less than the minimum value from any of these descendants of P. Okay, so here you have like a bunch of descendants. Okay, so D. Okay, so M of P is going to be less than the values of any of these descendants. Okay, so I'm going to write that this way, right? So right, and then M of P is going to be larger than the values of all of these descendants. Okay, so I'm going to write it like that. Okay, so this is like a lower and upper bound on what kind of values you can possibly encounter in this D among these descendants. Okay, now how do we get these values? Well, you don't need precise values for little m and big M. Okay, so you can just sort of approximate these or use any kind of estimate that you want. Okay, so for example, there's this problem called the knapsack problem, right? So like the knapsack problem is basically you have like a bunch of items, right? So each item has a, let's say, a value, right? So the ith item has a value and a weight, okay? And then you want to take a bunch of these items, and what you're trying to do is you're trying to, let's say, maximize the sum of the values, okay? So I know that we're talking about minimization problems, but anyways, these problems are symmetric to each other. So we're trying to pick a bunch of these items which have the maximum value possible. However, we need to stay within the weight constraint, so that so we're going to pick the set of items S out of all the items, okay? And we need to ensure that the weights of all these items is going to be less than or equal to some sort of constraint over here, okay? So you're only allowed to take like big W weight of items, and then for that weight you want to take as much value as possible. Okay, so in that problem, right, what we can say is that if we want, let's say, an upper bound, so let's say that we've already picked some set of items, okay? So that corresponds to, we're at some node P over here, where, P, we've already selected some items, right? So then the descendants are going to be, well, we're going to make choices among the untaken items, okay? So we can decide to which subset of the untaken items, undecided items we're going to take, okay? Right, and so there, if you want an upper bound on the maximum possible value of any of these descendant nodes, right, then you can just say that, okay, for all of the items I've not taken yet, right, I'm just going to take them all, okay? So that's definitely an upper bound on the value that I can get, right, for among these descendants, right? Maybe this might not be feasible because maybe these descendants, if I take them all, then the weight is too much. Okay, but at least the value is definitely an upper bound on all the descendants. Okay, so that would be a very fast heuristic to achieve one of these upper bounds. Okay, so now the branch and bound method is going to say that if I have two nodes, P and Q. Okay, so now let's okay, so let's take this out. Okay, and let's take another node Q, right? So this is D sub P, okay? So these are the descendants of P, right? And then this guy's got a bunch of descendants, so he's got D of Q, okay? So now if you have a situation where little m of P, okay, is larger than big M of Q, okay? Then what does that mean, okay? So little m of P is like the, so the minimum value among all of these descendants of P, okay? So little m of P is larger than the maximum value among all of these descendants of Q. Okay, and now remember we're trying to minimize the objective, right? So that means that if you look at any of these descendants of P, right, all of them are worse than any descendant of Q. Okay, because even the cheapest one among these, right, even the smallest one among these P descendants, right, they're going to be larger than the maximum descendant among these Q descendants. Okay, so in that case, we definitely do not need to look in P anymore, right? Because all of these, because Q right now is a feasible solution, right? And among his descendants, there are additional feasible solutions, right? And then all of them are going to be smaller than even the best possible feasible solution among P's descendants. Okay, so then we don't want to explore any of P's descendants. Okay, so then we can just eliminate this entire subtree over here. Okay, and now depending on how you define these two bounds, right, the upper and lower bound, right, then this can oftentimes help you prune a lot of these nodes from being explored. Okay, so that's the branch and bound heuristic. Okay, we're going to form these branches, but then you're going to produce these bounds on them, and then that's going to control which additional branching you do. Yeah, okay, right. So that's one sequential heuristic to help us navigate the search space and then do it efficiently. Another sequential heuristic is what's called A-star search. So A-star search is kind of like, so here we're trying to find a state with like the minimum value somehow, okay? And then we're trying to traverse a search space to do this. So the process is kind of like Dijkstra's algorithm. For finding shortest paths. Okay, so Dijkstra's algorithm, you start at some sort of source node, right, and then you can find the shortest path to any other node. Okay, so here our source node is going to be the root node of the search space. Okay, and the path we're trying to find, so we're trying to find the shortest path from let's say the source node to some other, let's say, objective node. Okay. And so Dijkstra's algorithm will let you find the optimal path, but it could be quite slow. So A-star search is an optimized version of Dijkstra's algorithm, which somehow like finds the most promising paths to search. Okay, and yeah. So the way it works is well, again, let's go with this example over here, okay? So suppose you're at this root node, this little pink node over here, okay? And you're trying to find a path to this blue node over here. So Dijkstra's algorithm is, and then your search space is just this entire grid, okay? So when you're at a node, you can search any of the neighbors of that node. So Dijkstra's algorithm is basically, it's going to search, it's going to look for this blue node, by sort of finding the closest by sort of finding the distance of each of these feasible nodes from the root node, and then it's going to search through these feasible nodes in the order of the distance. Okay, so it's basically going to form this like sort of spiral pattern around around the root node. Okay, yeah. So yeah, and then so yeah, so you're going to get the spiral, and then eventually the spiral is going to hit the objective node. Okay. However, the spiral is going to go through like a big chunk of the overall search space, right? And the reason is that Dijkstra's is sort of looking for the closest nodes to the starting node, and he keeps on sort of exploring nodes in the order of how close they are to the starting node. Okay. So it doesn't. For example, if you look at now, you can form like a sort of a circle of nodes like this. Well, this is not quite a circle, but anyways, it's this. All of these nodes have the same distance. You know, so if you're only allowed to sort of take these rectilinear paths, okay, where you can only go up, down, left, right, okay, then all of these nodes on this square, they have the same distance to the starting node, right? So Dijkstra's doesn't differentiate between any of these nodes, okay, and so therefore it's got to search all of these nodes, and then after that it's going to search sort of the next ring of nodes. Okay, so it's going to search everything sort of ring by ring in this spiral structure that I was showing. And this, of course, is very slow. Okay, so the way that A star search improves on this is that it's going to say that, well, some of these nodes are sort of better than others. Okay, some of these nodes are closer to the objective than others. Okay, so yeah, so what does it mean to be better? Well, this is where the heuristic part of A star comes in. Okay, so you have to define some sort of what's called an admissible heuristic function over here, which tells you which nodes you should be searching. Now, for some problems, it might be very hard to find an admissible heuristic. So in that case, A star search will not help you at all. Okay, because you don't have any sort of any way to tell which nodes are better than other nodes. Okay, but for other problems, you actually can find like good heuristics like this. And if you can find a good heuristic, then this can really cut down on the number of nodes that you need to search. Okay, so more concretely, Dijkstra's algorithm is going A star search rather. Okay, is going to have these three parts to it. So so for each node, we're going to compute a g of n, which is the cost from the root to that node. Okay, and then also we're going to have yeah. So for example, if you have a node over here. Okay, so then g of n is just going to be the cost to that node. So it's going to be the length of this path. Okay. Now h of n is going to be a lower bound on the cost from n to the solution or to a solution. Okay, so this is our heuristic. So somehow we need to come up with a lower bound on the cost from n to a solution. Okay, so for example, if we're going from this node to that node, right, then a lower bound on the cost would be maybe like, you know, you could compute the straight line distance from that node to the destination. Okay, so of course we're not actually allowed to go through these straight lines. We have to go, you know, in this rectilinear fashion. But the straight line is going to be a lower bound on the cost to the solution. Okay, yeah. So the first part over here, this is the g part. Oops. Write that a bit nicer. Okay, so this is the g part, and then this is the h part. Okay, and then we're going to define f just to be g of n plus h of n. Okay, so then this is going to be a lower bound on the cost of a solution to n. Okay, because in order to get to this node, for example, right, you have to pay a cost of g, and then after that, to get to the solution, you have to pay at least h. Okay, so f is equal to g plus h, and so that's going to be a lower bound on the cost on the cost through this node to get to the solution. And now A star search is going to look at all of these nodes. It's going to compute an f value for each node, and then it's going to look for the node with the smallest f value, and then it's going to expand that node. Okay. In contrast, Dijkstra's algorithm is going to expand the node with the smallest g value. Okay, so Dijkstra's, you're going to look at all of the nodes that you've actually reached from the root, right? And then you look at which one is the cheapest. Okay, and then you expand that node. You keep exploring from that node. Okay, so that's why if you have like a ring of these nodes over here, right? Then the problem is that all of these nodes have the same cost from the root. Okay, they all have the same G value, and so Dijkstra is going to expand, explore from all of these nodes. Okay, because it doesn't differentiate between these nodes. Whereas if you use A star search, right, then for example, if you look at this node over here, okay, well, it's got the same cost in terms of G, but it's got a larger F cost because because if you draw the straight line path over here, that's going to be larger than this H over here. Okay, so in that case, Dijkstra's will expand from this node and not from this other node. Okay, even though they have the same G cost. Okay, so yeah, so then A star search, right, can let you explore far fewer nodes. However, when you implement A star search, it's just like implementing Dijkstra. Okay, it's very easy to implement. So you need to keep a list of nodes that you've already explored. Okay, so these are the nodes that you have the G values for. Okay, and then you have to keep this open list of nodes which you have not explored. Okay. And now for each of these open nodes, you're going to compute this F value. Okay? And then you're going to look for the node with the smallest F value, and then you're going to explore that node. And when you explore that node can potentially have get a new cost, right? And then and then you have a new F value for that node, and so you're going to update all of these values. Okay, so so the A star search is guaranteed to find you the minimum cost solution. Okay, as long as you use this admissible heuristic. Okay, so this H here has to be a lower bound. Okay, it cannot be larger than the cost from n to the solution. It has to be less than or equal to the cost from n to the solution, from a node to the solution. Okay. And if you have a good H. Okay, so what is a good H? A good H is if H exactly equals the cost from n to the solution. Okay, then that would be perfect, right? Because that would just then F would exactly be the cost of this node. Okay, because you have the first part, that's the cost to get to G, right? And then you have the second part, which is like the exact distance from n to the solution, right? Then you can just pick the minimum out of all the nodes. You pick the one with the minimum F, and that is exactly the node with the minimum cost that you need to go through. Okay. Right. However, it's hard to get such a good admissible heuristic, right? So then we're just going to settle for a trade-off between how quickly we can compute a heuristic versus how close it is to the real cost of a solution. Okay, and the closer it is to the real cost, the faster we can execute for. Okay, so let's do an example of this. So let's again do this 8 puzzle. Okay, so for this 8 puzzle, one possible admissible heuristic is that let's say that you start with this configuration over here. Right? So eventually you want to end up in this other configuration, right, with everything in order. And so we need to figure out like how an admissible heuristic would be how many moves does it take to go from this configuration to that configuration? Okay, what's the minimum number of moves? Well, we don't actually know the minimum number of moves, but we do know that if some of these tiles are out of place, right, then to get to the correct solution, we at least have to move those tiles. Okay, so for example, the 7 here, right, this is out of place. Okay, so at least you have to make a move for 7, right? You have to move at least move 7 once. Okay, the 6 is out of place, so at least you have to do 1 move for 6. Okay, so then therefore, if you just add up how many tiles are out of place, that gives you a lower bound on how many moves you need to make in order to get to this correct solution here. Okay, so in this case, we would need to make, so this guy's out of place, right? So 1, right, 2, 3, and then 4 moves. Okay, at least you have to make 4 moves to get to the correct solution. Okay, so that's like a simple heuristic. You can slightly improve on that. So you can say that not only do I have to move, let's say node 7, right? I have to, so because 7 is going to end up over here, then at the very least, I need to move 7 twice. okay, because otherwise I can't get 7 from this position to that position, okay? So, so therefore, I can actually count the distance. So for each node in the current configuration, I can look at the distance of that node, the number of moves required in order to get that node to the correct position. And then I can add that up over all of these tiles. Okay, so for example, yeah, so let's sort of zoom in over here. Oh, okay. All right, so let's try to zoom in. Okay, so well, all right, so good. All right, so but I can't write once I zoom in. Okay, well that's not useful. So yeah, so what I'm trying to show over here is that you know, for this node, sorry, for this tile 7 here, right, you need to move it to this position. So therefore, you need to make 2 moves for this guy. Okay, so these guys, 2, 3, 4, are in the correct positions, right? So we don't need any moves for those. The 6, you need to make 1 move, right? The 5, you need to move. You need to make 1 move. The 1, you need to make 2 moves, right? And the 8 is already in the correct position. Okay, so therefore you can estimate that the number of required moves from this position to the a lower bound on the number of required moves from this configuration to the correct configuration is 6. Okay, so that's what's being shown over here, right? This is an admissible heuristic. This value over here. Okay. And so the way that we would conduct a star search is that we would compute this value, right? This estimate of moves, okay, for every node, and then the f value for node is how many steps that we take to get to that node plus its admissible heuristic value. Okay, so for example, this guy, right, his f value will be 8 because it took 1 move to get to this node, plus his h value over here is 7. Okay, this guy also has f value of 8. Okay, and then the A star algorithm is going to expand nodes in order of their f values. So in this case, we have a tie over here. So so therefore, we can expand either one. So let's say you expand the left one, right? If you expand the left one, then you get 2 nodes over here. And so this guy has this guy has an f value of 2 plus 8, right? His h value is 8. So then he's got an f value of 10. And then this guy's got a f value of 8, right? Because it took 2 nodes, 2 moves, and then he's got a heuristic value of 6. Okay, and this guy also has a f value of 8. So then again, we can choose, so we have a tie on the 8, so we can choose either one to expand. Let's say that you expand this node over here, right? So then each of these guys would have, so now their f values would be, well, they took 3 moves, right? And then they have a heuristic value of 7, so they all have f values of 10. Okay, so so now since these guys all have f values of 10, and this guy has f value of 8, right? Then we would expand him. Okay, and then yeah, so you just keep applying this process, and then so this can actually dramatically decrease the number of configurations that you have to search through. Okay, so you know, if you don't, well, I mean, for this small problem, right, for the 3x3 tile problem, there are actually not that many states that you need to search through, but you can make larger versions of this problem. So if you make like 4x4, right, then you know, potentially there are like, you know, millions of configurations that you could search through. But if you do this A star heuristic, then this can cut it down to like maybe a few hundred or a few thousand or something. Okay, so sometimes you can also, if you want even faster speed, okay, then you can use an h function that is slightly larger than the cost from the node to the goal. Okay, so when you do that, you can further reduce the number of nodes that you search through. However, you're no longer guaranteed that you produce the minimal solution. Okay, so this can produce a somewhat suboptimal solution, right? So so you know, if h can be much larger than the actual cost, then this can produce a very suboptimal solution, right? So the degree of suboptimality is based on like how close h is to the actual minimum cost. Okay, and the final sequential algorithm that we'll talk about is DFS. Okay, and there are also variations on DFS. Okay, so DFS is just it's a depth first search. So depth first search is just that if you have a search graph, right, then we're going to search sort of as deeply as possible into this search graph. And then for each node that we're at, right, we're going to explore its neighbors. And then we'll try to explore those neighbors sort of as deeply as possible. And so a way that we can represent this process is we can use a stack. And then whenever you're at a node, right, you're going to take all the neighbors of that node, and then you're going to put it onto the top of the stack. And then you're going to, the next node that you explore is going to be, again, the top of the stack. Okay, so for example, if we're in this search process right now, and suppose we've already got these nodes in our stack. Okay, so these are basically the unexplored nodes. So they're the leaf nodes, right? Like the 23, 24, and so on. Okay, so we got all those leaf nodes in the stack, right? And then if we're currently at this 22, and suppose this guy has some more neighbors, right? So he's got a neighbor, let's say 25, and then 26, right? Then we would put 25 and then 26 into the top of the stack. And then we would pick one of those nodes. We would pick the top of the stack out, right? Let's say node 26, right? And we would further explore, right? And then if node 26 doesn't have any further neighbors, right? Then we backtrack from 26. So we go back from, so we pop 26 and we explored him, but he doesn't have any neighbors. So then we pop him and then we go back to 22, right? We backtrack to 22 and then we pick the top of the stack again. So in this case, 25. Okay, and we keep exploring from 25. Okay, so that is the traditional DFS. It can be implemented using a stack. So there are some variations on DFS. So for example, there's you can combine DFS with branch and bound. Okay, so some of these so branch and bound says that for certain nodes you don't need to explore them because all of their descendants are like bad, right? They won't help you optimize. Okay, their values are too large. So you can use this pruning process of branch and bound, and you can combine that with DFS. Okay, so there's also what's called iterative deepening A star. Okay, and the idea here is that so this is basically like DFS, except for the problem with DFS is that because it's depth first, it can go very deep into the tree first, right? So here you see that we've gone very deep into the tree, and we're not really exploring. So we've gone very deep into the tree, but we're not exploring the top parts of the tree. Okay, so it's possible that a good solution exists near the top of the tree. Okay, this depends on the problem, of course, but in some cases, you have good solutions near the top, and so DFS is not going to find them, and so the way iterative deepening is a way to find these solutions up top. So the way it works is that we're going to do several rounds of DFS. Okay, in each round, you put a limit on how deeply you explore. Okay, and as you do more rounds, you allow yourself to explore deeper and deeper layers. Okay, but initially you explore the top of the tree. There are different ways of implementing this. One way is that you can put an upper bound B on the cost of what you're willing to explore. Okay, so for the current round, you put an upper bound of B. Okay, and in this round, if you ever get to a node where the F value, so the F value comes from the A star estimate of the node. If the F value is larger than B, then you're going to backtrack. Okay, so yeah, so you don't keep exploring from that node. You only keep exploring as long as the F value is not too large yet. Right? Okay, so this limits you to like certain layers of the tree. Okay, but if you don't find any solutions in those layers, right, then you want to search deeper, and so therefore you need to increase this upper bound. Okay, and you can increase this in different ways. One is that you can set it to like in the previous round, the unexplored node with the smallest F value from the previous round. Okay, you can set that to be your B value for the next round. Okay, and initially, your B value is just like your root. The F value for your root. Okay, so yeah, so this is one way that you can implement iterative deepening. Okay. Yeah, and then there are other heuristics for pruning these search spaces. Okay, there's like cutting plane methods and other methods. Okay. But now we're gonna go back. So all of these things are sequential heuristics. Okay. So now we're gonna look at how to implement these in parallel, and we're gonna see what kind of problems can arise when you do this in parallel. Okay, so the reason you need to parallelize is that these search graphs can be very large. Okay, and when you parallelize, you're going to have some sort of overhead. So the overhead can be several sources. There might be communication overhead between your different processes. Okay, you could have load imbalance between the processes, and these processes sometimes need to share some data structures. So there can be contention on these data structures. Okay, yeah, and also something which is kind of interesting when you parallelize is that if you search sequentially, you're going to search through the tree in a certain order, right? But when you search in parallel, you could be searching different parts of the tree that you would never even bother to search in the sequential ordering, okay? Or that at least you would. So the sequential search order and the parallel search order can be quite different from each other. And in certain cases, this can this can either make the parallel search more efficient or less efficient than the sequential search. Okay, so we'll see some examples of that later. Okay, so in particular, if you let WS be the number of nodes that you search in your sequential algorithm, okay, and WP be the number of nodes for the parallel algorithm, then you can have this search overhead, okay, which is WP divided by WS. And so this overhead can either be larger than 1 or equal to 1 or less than 1. Okay, so if it's larger than 1, then somehow this parallel search is less efficient than the sequential search, right? Because you do more work overall in the parallel search than the sequential search. Okay. However, there are cases when it can be less than 1. So if it's less than 1, then you actually do less work in the parallel algorithm. Okay, so and we call this like a speed up anomaly, right? Because usually the parallel algorithm has to do at least as much work as the sequential algorithm. Okay, but in this case, since we we have a fixed problem and we have different search orders, then actually the parallel algorithm can do less work than the sequential algorithm. Okay. Okay, so we'll see some examples of that later. Right. So now let's get to how to parallelize particular ones of these search algorithms. So first of all, DFS. Okay, how would you parallelize DFS? Okay. So what you so remember the way we implement DFS sequentially is that we use a stack. Okay. So in order to parallelize this, we're just going to assign different parts of this DFS stack to different processes. Okay, now a problem with doing this is that, or the first problem that with doing this is that if you just use a basic assignment, okay, then you could have very poor load balancing. So for example, suppose at some point in the stack you just have you have let's say these nodes and then these nodes. Okay, so then at that point, if you want to subdivide between two threads or two processes, right, you would just give each, let's say, 3 nodes. Okay, but it's possible that in this in this left branch over here, right, this is a very small branch. Okay, so even though you've assigned 3 nodes, as you keep exploring, there are no additional nodes in this branch. Whereas for the other branch, for the one on the right, this can be a very deep branch, and there can be many nodes in the descendants, among the descendants. Okay, so in that case, you get a very poor load balance. Okay, and when you first made this assignment between these two processes, right, you don't really know which one is going to have a large subtree or which one is going to have a small one. Okay, yeah. So in general, if you just assign statically, if you do this assignment once, you could end up with a very bad load imbalance. Okay, so instead, we're going to do dynamic load balancing. Okay, so dynamic load balancing says that even if you made a bad load balance decision in the beginning, right? So once you now start to expand this this B part, right, and you see that there are many nodes over here, then you're going to readjust your load balancing. Okay, you're going to give some of these nodes back to the first process. Okay, so how do you do this dynamic load balancing? Well, remember that we talked about this algorithm called work stealing. Okay, so work stealing, the way it so the way that work stealing worked was that each thread maintained a queue of work that it did, right? That it still has to do. Okay, a queue of tasks that it still has to perform. Okay. So in this case, your queue would just be all of the items in your stack. Okay. All right. So that's the amount of work that you still have to perform. And if a node ever if a process ever runs out of stuff to do, okay, so its queue becomes empty, it just goes to another process's queue and then takes some stuff out of it. Okay. And because it doesn't know which other process has stuff in its queue, it'll just go to a random other process and then take some stuff out. Okay, or some arbitrary process, right? So we have some way of selecting who to go steal from. Okay, now when you do this work stealing, one thing you have to control is how much you're going to steal. Because each time you do the work stealing, you're going to have to communicate with a remote process, right? You have to take the tasks from that remote process, and then also you might need to do some synchronization on the work queue of that remote process. So, if each time you only steal a small amount of work, right, and then you do that small amount of work quickly, and then you have to go steal again. So then you have to steal many times. Okay, so that's a lot of overhead, right? So if you steal too little, you have too much overhead from the stealing. But if you steal too much, right, then you could have poor load balancing. Okay, because because if you if the other guy only has a certain amount of work and you steal like almost all of it, right, then it's no longer load balanced. Okay, so you have to control, you have to find like a trade-off between these two things. And also you have to decide who you're going to steal from. Okay, so one way is that you can just steal from a random other process, right? But there's some other ways that you can select this. So for example, there's one method called asynchronous round robin. So here, now the node that you steal from, let's call this guy the victim, right? The process that you steal from, it's the victim. So here, in the asynchronous round robin, each processor is going to choose its victim independently, okay? And then it's going to round robin through all of the processes, through all the potential victim processes, okay? So for example, if I choose to, I choose an initial victim, let's say process 3. Okay, if that guy doesn't have any work, or if he doesn't have enough work, right, then I just round robin through the other nodes. Okay, so I go 4, 5, 6, and then maybe I wrap around to 1 or something. Okay, and then another process can choose its victims independently. So maybe he starts with process 5. Okay, and he tries the processes like 5, 6, 1, 2, 3, 4. Okay, so that's asynchronous round robin. So there, the advantage is that the processors don't need to do any synchronization with each other, right? Because they choose their victims independently. Another method would be a global round robin. So here, all the processors are going to maintain like a common victim, okay, in a global variable. And then each time any processor takes from that victim, right, he's going to increment that variable. Okay, so in this case, we're all going to decide to like steal from process 2 first, let's say. Okay, so if I steal from process 2, then now I'm going to change the victim for the next time to be process 3. Because I don't want to keep stealing from the same process over and over, right? Because once I steal from him, then he's now got, then he doesn't have that much work left anymore. So next time, I don't want to steal from a guy that doesn't have much work. I want to steal from somebody else. Okay, so after I've stolen from 2, I'm going to change this global variable to 3. And so next time if you steal, right, you're going to steal from 3 and then change it to 4 and so on. Okay, so then we're just going to round robin through all of the processes, but each time all the processes need to synchronize in terms of who to steal from. Okay, and then finally, this randomized work stealing is the one that I talked about earlier. Okay, where you just every node just randomly picks a victim. Okay, so he doesn't round robin through all the victims. He just sort of picks victims randomly each time. Okay, so something else about work stealing is that Now we said that you don't want to steal too small amounts of work, right? Because that you pay an overhead for doing that, but then you don't get much work. You don't actually get much work from the victim. Okay? So therefore, we can set a cutoff in terms of how much work you're going to steal. Okay. So for example, in the search tree, we can set a cutoff depth. Okay. So if a node doesn't, if his remaining work is his remaining amount of work is below a certain depth, then we don't steal from that node. Okay. So we only steal large chunks of work from other nodes. Okay. So let's look more deeply at this at the overhead that you pay when you do this work stealing. Okay, so work stealing is actually a very popular method that people use in practice. So let's try to figure out how much overhead there's going to be. Now we can't do this in a very precise way because the workload is being generated dynamically, right? So we don't really know. We don't have precise information. So we're going to make some simplifying assumptions. Okay. So the first assumption is that if you steal from a processor and he's got, let's say, W amount of work, okay, then after stealing, both the original processor and the stealing processor will have at least alpha times W amount of work for some constant alpha. Okay. So for example, if alpha is let's say 1/2, okay, so that means that each time I steal from you, I'm going to take half your work. Okay. It doesn't have to be exactly 1/2. It can be like, let's say, a quarter. Okay. So then after that, I have a quarter of your work and you're left with 3/4. Okay. But you don't want alpha too small, right? I don't want to just take 1% of your work, right? Because I paid this overhead, so I want to get more work from you. Okay. So there's some constant alpha where both of us have at least alpha amount of work after the work stealing. Okay, so then, all right, so then this also says that, so because the other processor, the victim, only started with W amount of work, right, then this means that after work stealing, both of us have less than 1 minus alpha times W amount of work, right? Okay, so the other assumption is that we don't want to steal tiny amounts of work. So if a processor has, let's say, less than epsilon amount of work for some small epsilon, okay, then nobody will steal from that processor. It doesn't do load balancing. Okay, so now we can figure out how many times nodes are going to steal from each other. Okay, so the way to do this is suppose we have P processors, okay, and let's let V of P be the total number of steals, okay, among all of the processors. So all P processors are potentially stealing from other processors. So V of P is going to be the total number of steals before every process receives one steal attempt. Okay, so all processors are doing steals, right? And then so they're going to steal from some processes, but maybe not other processes yet. But as you do more and more steals, right, then eventually every processor will be stolen from, will become a victim at least once. Okay, so V of P is how many steals does there have to be in total before every process becomes a victim? And this depends on which work stealing algorithm we're using. Okay, so we're going to use this V of P parameter to sort of compare these different work stealing algorithms to see which ones are more efficient. Okay, so then now one thing is that suppose that at the current time point, the maximum amount of work at any processor is W. Okay, then if we do V of P steals, right, then that means that every process will become a victim at least once. And whenever it becomes a victim, right, then that process will end up with less than 1 minus alpha times W amount of work. Right? So even the processor with the biggest amount of work, okay, after V of P steals, he's going to become a victim at least once. And then after that, he's going to be left with at most 1 minus alpha times W amount of work. Okay. All right. So then, so then after this number of steals, the maximum amount of work at any processor is going to be at most this value. And so that means that if you do another V of P steals, okay, then the maximum amount of work is going to be 1 minus alpha times this value here. Okay, so 1 minus alpha squared times W. Okay, and in general, if you do K times V of P steals, okay, then the maximum amount of work is going to decrease k times, and each time it's by a factor of 1 minus alpha. So we're going to have it's at most 1 minus alpha to the kth power times w. Okay, and remember that we're going to keep doing work stealing until all the processors have just a tiny amount of work. And then after that, we're going to stop work stealing, right? Because if you just have epsilon work, then there's no point doing the work stealing. Okay, so the question is, how many times do we have to do work stealing before the maximum amount of work at any processor is less than epsilon? Because once we reach that point, then the work stealing algorithm will stop, right? Then nobody will do any more work stealing. Okay, yeah. So the question is, all right. So then, since if we do k times VP steals, okay, then the maximum amount of work is going to be this in the system. Okay, so then we just need k to make so the bigger k is, right, the smaller this maximum amount of work. Okay, so we just need to choose k large enough so that this thing becomes less than epsilon. Okay, and so you can see that if you make k be this value, right? So here we basically take the log of w divided by epsilon. Okay, then we're going to end up that the maximum amount of work is going to be less than epsilon, and so the total number of steals that we do, right, is going to be k times v of p steals for this k. Okay, and so therefore the total overhead that you paid, right, was so this thing we're just going to ignore these constant factors over here, right? So and let's say that for each steal you pay like some sort of constant communication cost. Okay, you pay a fixed amount of communication cost. So in that case, the total overhead from the work stealing is going to be like this. Okay, and the total efficiency of the algorithm. Okay, so now we want to figure out which of these work stealing algorithms is more efficient. So the efficiency is going to be, well, this work stealing stuff, this amount of work, right? This is involving communication. So we're going to multiply this by the communication time, right? And then this is the overhead that you pay for the work stealing. And then we divide that by the actual work that you did. Okay. And then, we want this ratio to be small here, right? We want the efficiency to be, you want the overhead to be small. And so, in fact, if you want constant efficiency, right, then you have to make sure that whenever this top term increases, that you also increase W so that this entire fraction over here is constant. Okay, so now we're going to look at different work stealing types of work stealing algorithms, and we're going to see how large each of these, or how efficient each of these is. Okay, so first, if you look at the asynchronous round robin, okay, so now how many steals do you have to do before every process becomes a victim? Well, so you have to do at least p steals, right? Because you want every one of the p processes to be a victim, so you have to do at least p steals. But you might need to do up to p squared number of steals, okay, in order for every process to become a victim. Because, for example, if you so let's say that you have these processes, right? So you have process p. Okay. Now for the asynchronous round robin, every process is going to pick the victims independently. Okay. So it could be that initially, like all of us pick this guy as our victim. Okay. And then, and then next, we're gonna round robin through all the processes. So then we're all gonna pick this guy as a victim, okay, and then so on. And so it's actually gonna take like p steps before each of us, before all of us pick this guy as the victim, right? And so, for each of these steps, we have these these p different steal attempts, right? So we have a bunch of steal attempts for each of these nodes, until eventually we all try to steal from this final node. Okay, so it's p steals per step times p steps, so that's going to be p squared steal attempts in total. Okay, all right, so then so this is the number of steals, and in order for us to have constant efficiency, we need the amount of work to be proportional to the amount of overhead. Okay, so you need this W here to be omega of this thing, right? And then since you have V of P is at most P squared, you have that W is going to be omega of P squared log P. Okay, so you need a pretty large amount of work in order for this algorithm to be efficient. Okay, for a global round robin, right? So since we now for global round robin, we have a common victim variable, right? And we keep increasing that every time somebody steals from one node, right? So therefore, if somebody steals from 1, right, then the next time somebody else will steal from 2, and then 3, and then so on. And so in P steps, okay, we're going to make sure that we that every node becomes a victim. Okay, so V of P equals P. Okay, right, and then so in total, since the overhead that we pay is going to be V of P times log W, right? So in total, this victim variable, right? We're going to need to access this victim variable P times log W times, because you have to access the victim variable every time you get a victim, right? And then every time you do a steal, okay? And in total, we're going to be doing that number of steals. Now the problem is that this victim variable, this is being shared between all of the processes, okay? So therefore the total time to access this variable, since you access it this number of times, right? Since it's a shared variable, then the total access time is going to be just the number of times that you access it. Okay, so now for efficiency, you want each process's execution time to be at least the overhead that you pay to access this shared variable. Okay, so for each process, its execution time is going to be, assuming the processes are perfectly load balanced, then the total work is going to be W. So each process is going to do W divided by P amount of work. Okay, and you want this stuff done by each process to be at least the time for accessing the variable. Okay, so so if you do this, then you have that you're going to end up with again, W is going to be omega of P squared log P. Okay, and lastly, for the randomized work stealing. Okay, so here you can actually you can prove that if you set if you make this number of steal attempts, okay, so basically P log P steal attempts, okay, then every node will become a victim once with high probability. Okay, all right. So so for randomized work stealing, V of P is going to be this, and in that case, the total work is going to be just V of P times log W, and in this case, we have that W is going to be omega of P times log squared of P. Okay, so you see that for randomized work stealing, here this is more efficient than the asynchronous or global round robin methods, right? Because these both involve something like P squared, right? And this is just like P times log squared of P. Okay, so so they did some experiments on this. For example, they compared these 3 methods, and they got that if you use this, let's see, which one is which over here. Okay, so if you use asynchronous round robin, okay, so as you increase the number of processors, you're measuring the speed up. Okay, so the higher this line is, the better it is. Okay, so the global, let's see, so this is the asynchronous round robin. Okay, so this it's scalable up to maybe 500 processors. Okay, but beyond that, the cost to accessing the cost for the work stealing is going to be too large, and so the speed up here is going to plateau. And then for the global round robin, in fact, as you increase the number of processors, eventually the speed decreases, okay, because you have this common victim variable, which is being accessed by all the nodes, all the processors, and this is too much overhead. And then the best performing one is the randomized one. Okay, so this one just keeps scaling. Okay, because because you pick random nodes, and so that's there's no contention, and there's not too many work steals either. Okay, so next, okay, we can talk about parallelizing a depth first branch and bound, or the iterative deepening method. Okay, so in order to do the depth first branch and bound, then you have to store the so for branch and bound, you need to have these bounds on the values of different nodes. Okay, so we're going to store the globally best solution, and then if a processor finds a better solution, it's going to update everyone by doing a broadcast. And probably the best solution is not going to change that much. It's not going to change very often, right? So even though we're doing a broadcast, each time we find a better solution, we're probably not going to pay too much overhead just because the solution doesn't change that much. Okay, and then for the iterative deepening, when you do the broadcast, so remember for iterative deepening, for each round, we need to have this bound, right? This we're only going to search up to the cost being a certain bound, and then we're going to start the next round of this IDA, right? So yeah, so then we need to just do the broadcast for the bound for each round, okay? And then once we have that bound, then we're just doing a DFS in that bound, okay? And then we can just use the parallel DFS algorithm that we had previously, where you sort of dynamically divide up the stack. Okay, so for A star, okay, so A star, we can also parallelize this, but for the A star, we have this queue of F values, this priority queue of F values, right? So remember that we have to search through the F values in order of increasing F values. So we put all these F values in a priority queue, and the processes all have to access that priority queue. Okay, so we need to parallelize the accesses to that queue. Okay, so when you do this with P processors, then in order to parallelize this, so there's actually just one minimum value in that queue, right? So if all the nodes just try to get that minimum value, right, they would all be contending on that one minimum value. So instead, since we have P processes, we're going to expand the P smallest values in that queue. Okay. Yeah, so this is going to be different than so it's going to expand a different set of nodes than the sequential algorithm. Okay, because the sequential algorithm always expands the smallest node and then adds some more nodes potentially into the queue, and then it keeps picking the smallest node. Okay, so here we pick at any time point we just pick the P smallest nodes, and this could actually be different from what happens in the sequential algorithm. So this can end up doing like more work than the sequential algorithm. Okay, the other problem is that since we all have to take out these P nodes, right? We have a contention when we access this, when the parallel processes access this queue concurrently. Right, so a way that we can deal with that is we can give each processor its own copy of the queue. Okay, and now so we try to keep these different copies more or less synchronized. Okay. So that means that if a process finds a good node with a small f value, right, then it should tell the other nodes about this good node, okay? Because if it doesn't tell the other nodes, then the other nodes are still they're still going to work on nodes with bigger f values, okay? So they're going to expand these nodes with big f values that they don't really need to expand, right? So so we do need to do some sort of communication to communicate these small f values, but we don't want to do too much of this. Okay, so yeah, so we're going to somehow find a trade-off between how often we update the other nodes about these improved f values versus how much communication that's going to cost. And another problem is that if the search graph is not a tree, then we saw that you could sometimes visit the same node several times. Okay, so in this case, we need to detect when we visit a node several times. And so we said that we could use a hash table for that, but if you parallelize, then you can also distribute this hash table among the processors. Yeah, so okay, so this is going to have some communication, but if we do, if you have a problem where you can actually do a lot of computation per node that you search, okay, then the communication cost is not going to dominate the overall computation. Okay, so for the final part of this, we're going to talk about these speed up anomalies that you can have. Okay, so this is where when you search in parallel versus when you search sequentially, you can sometimes do more work, but sometimes you can do less work. Okay, so and this comes about because because basically we're using different algorithms. when you search in parallel versus sequentially, right? So to give an example of this, suppose you have this situation on the left, okay? And suppose you do a sequential search, right? Now, let's say that this is the order of the nodes that you search in, right? So you start here, and then you search 1, 2, 3, just in this order. And let's say that the goal you're trying to end up at is going to be this final 13th node over here. Okay, so the sequential algorithm is going to take 13 steps. Now, if you search in parallel, right, then you're going to assign these nodes. Let's say that you have two parallel processes. Okay, then you're going to assign some of these nodes to each process. Okay, so in the beginning you just have one node. Okay, so let's say that you have one process doing this, and then after that you're going to split into two nodes. So now you're going to have both processes executing. Okay, so for example, the first process, right? Let's say it explores the nodes in this order, right? 2, 3, 4, 5. Okay, the other node is going to explore like in this order. Okay, 1, 2, 3, 4. And so suppose the two processes are running at the same speed. Okay, then what happens is by the time the first process gets to this node, right? So it's explored 4 nodes. The other process also explored 4 nodes, and it already reached the goal node, right? So after so in total it took 5 time steps before you found the goal. Okay, right? Because this is 1 time step, and then in parallel you run 4 more time steps, and so you found the goal after 5 time steps. Whereas for the sequential algorithm, right, this took 13 time steps. So in this case, the speed up is actually going to be 13 divided by 5. Okay, so that's more than 2. So even though you're only using 2 processes, you get more than a factor 2 speed up, because you're not searching in the same order in the sequential versus the parallel setting. Okay, so yeah, so sometimes people call this an acceleration anomaly. Okay, so you can get the opposite situation. So now suppose the goal is over here. Okay, then the sequential algorithm would just search 7 nodes to get to the goal. Okay, however, if you search in parallel, right, then the number of steps you need is let's say so this is 1 step, and then after that you can search in parallel. But you see that this left thread over here, right, he's going to have to take 6 more time steps, okay, before he finds this this node. Okay, so therefore yeah, so the sequential search algorithm only explores 7 nodes in total, right? Whereas the parallel algorithm explores 12 nodes. Okay, so the parallel algorithm actually did more work than the sequential algorithm, and you can call this a deceleration anomaly. Okay, so then so then lastly, let's look at when it's more efficient to search in sequentially versus in parallel. Okay, so we're gonna have we're gonna create a model for searching using DFS. Okay, we're gonna try to derive the average speed up in that model. Okay, so what we're gonna assume is that suppose you have a search tree and it's got m leaves. Okay, and suppose all the solutions that you're looking for are at the leaves. Okay, and there's at least one solution. Okay, so some of the leaves are solutions and others are not. Okay, and let's say the tree is such that the number of nodes that you search through is proportional to the number of nodes, number of leaves that you explore. Okay, so you might need to explore some internal nodes, but let's assume that the number of internal nodes is proportional to the number of leaves that you explored. Okay, so then we're going to compare a parallel DFS algorithm with a sequential DFS. Okay, so the parallel DFS algorithm is going to take the tree and then divide it into m equal parts. Okay, and then it's going to assign, so let's say you have m processors, and then it's going to assign 1 processor to each part, and assume the processors run at the same speed. Whereas the sequential DFS algorithm, it's just going to okay, so it's going to still have these partitions, but it's going to order them randomly. Okay, so it's going to take a random order on these m partitions, and then it's going to completely search 1 partition before it starts searching in the next partition. Okay, right. So now assume that in the ith partition, each leaf has some probability of being a solution, okay? And assume these probabilities are independent. So let's say that in the ith partition, right, every leaf has a probability of row I of being a solution. All right, and both the sequential and the parallel DFS algorithms are just trying to find one solution. So as soon as it finds one solution, they can it can stop. Okay, so now let's look at which one is going to be faster, searching in parallel or which one is more efficient, searching in parallel or searching sequentially. Okay, so if you search in the ith partition, right, then since each node has an independent probability row of I of being a solution, right, then the number of leaves you need to search in that partition before the expected number of leaves you search before you find a solution is just going to be 1 divided by this row of I. Right? Like if each node has a 1/10 probability of being a solution, then in expectation, you're going to search 10 nodes. Or 10 leaves, rather. Okay? And so therefore, the expected running time of the sequential DFS algorithm, okay, is going to be this expression over here. Okay, it's 1 over m, right? So that's the number of different partitions times 1 over row 1 plus 1 over row 2, and so on. Okay, so the reason this is true is because the sequential algorithm is going to take a random partition. Okay, and if it picks the ith partition, then the expected number of leaves it needs to search through is 1 divided by row I. Okay, so therefore the expected time for the sequential algorithm is just the average of all of these values, because it's going to pick a random one of these partitions, and each partition has this sort of search time. Now, for the parallel DFS algorithm, right? So in that case, since we have m processes running in parallel, then in each time step, they're going to be searching through m different leaves at the same time in parallel. Okay, and as long as one of those leaves is a solution, right, then the parallel algorithm can stop. So the only case in which it does not stop is if all m leaves that the processes are searching, all of them are not solutions. Okay, so what is the probability that all of these things are not solutions? Well, it's going to be this expression over here. Okay, because we're assuming all these leaves are independent. So the probability that in the ith partition that the leaf is not a solution is going to be 1 minus row I. Right? And so the probability that all of these leaves are not solutions is going to be the product of all of these 1 minus row I's. And the probability that at least one of them is a solution is just 1 minus this probability. Okay, so assuming the rows are small, then this quantity over here is approximately equal to the sum of all of these rows. Okay, so therefore the expected running time of the parallel algorithm, okay, is going to be this, because for each time step. For each time step that the parallel algorithm runs for, there is this probability that one of the leaves is a solution, right? So therefore, the expected number of time steps you need to take before you find a solution is going to be 1 divided by this quantity. Okay. However, so that's where you get the denominator from. However, in every time step, you have m processes running. Okay, so they're actually doing m parallel steps. And so that's why you need to multiply this by m. Okay, so that's the total work. Sorry, that's the expected amount of work that the parallel processes are doing. Okay, so now we can compare the sequential and the parallel search algorithms. So for the sequential, so let's see. So for the parallel one, right? So this is just this quantity over here is just equal to 1 divided by the arithmetic mean of these values. Okay, so the arithmetic mean is just you add up these values and you take their average. Okay, so the parallel running time, the parallel work is just 1 divided by that. Okay. For the sequential algorithm, right, so there's something called the harmonic mean of these things, right? So the harmonic mean is basically you do, so you have m values over here, so you do m divided by the sum of all of these inverse things, okay? But here we have 1 divided by the harmonic mean, Okay, so this is 1 divided by the harmonic mean. Okay, so there's this inequality between the arithmetic and the harmonic mean, which is that the arithmetic mean is at least as large as the harmonic mean. Okay, and so that would mean that this Wm here is going to be no larger than the Ws. Okay, so the work for the parallel algorithm is going to be no more than the work for the sequential algorithm. And in fact, the only case where they're equal is if all of these partitions have the same probability of having solutions. Okay, so if all the row i's are equal, then the sequential and the parallel algorithms have the same total work. Okay, but if the row i's are not equal, right, then we're going to have that the parallel algorithm is actually going to do less work than the sequential algorithm. Okay, and so in that case, we're going to get a superlinear speedup. Okay, so if the solutions are not sort of equally distributed among the search partitions, then you actually can do less work when you search in parallel versus when you search sequentially. Okay, so that's all we have for this lecture. See you guys next time.